the table. And while they're doing that, let me let you know that just after the panel session, we're going to be awarding the prize for the Startup Showcase. So you want to stick around for that. The $5,000 prize. Rody and Schwartz will be making that award. So the format here will be like the morning panel session. Kris will start us off with a few slides, an introductory statement, and then we'll go along down the line. Kris is from the Southwest Research Institute, and I had the privilege of being at a conference with him a couple of months back and found that he was given the best paper, overall paper for the conference award for a system that he's going to describe to us. So take it away, Kris.
All right, thank you, Todd. The topic for this panel was the daunting demands of vehicle sensing. So, this is easily something that we could spend days talking about. So I'm going to talk about some specifics here, but it's worthwhile to start at the top. So you might ask the question, and I think it's been answered in a number of ways today, but what's really so hard about this? I mean, if you go out on the streets around Austin, you will see Google cars driving around. So there's certainly a proof of concept that it's possible to drive autonomously on the road. But then you think about it a little bit, and there are challenges if you just look in an individual dimension that you can introduce that those types of vehicles and systems will fail with. Now, this is pushing several dimensions here. So, for one, if you go off-road, that's a challenge that's not readily solved these days. If you go where there's snow, that's still most people admit that that's a challenge. If you go to high speed, where there are significant vehicle dynamics, those are all real challenges. And some of you that are, keep up with the news may say, well, that there are research groups and organizations, companies that are solving some of these problems. The Race Up Pikes Peak, autonomous race cars. But that's not really the problem here. Any specific challenge we have ways of solving. But what we're talking about is really this other one. It's like you're driving through, on this race course in the snow, and then a baby somehow crawls out across there. I mean, that's a joke for this, but the reality is that it's not dealing with the things that are obvious or clear. It's in a lot of cases the anomalies that will cause the problems. And one of the things that occurs to me or makes me wonder, because I think about this a lot. I've worked in this area for just over 10 years now. Is will we really have to get to the point where these autonomous systems basically have biological or human-like perception capabilities? And there are some ways to push vehicle automation forward, particularly in the sensing domain, because there are some significant advantages that automated vehicles have. So let's look at first the obvious case for sensing. It's the live or active perception that you have with a vehicle. And this is one that corresponds most directly to human experience. So when we look at, compare one-to-one human drivers with computers or cars, humans are much better analyzing images, even to some extent analyzing, for example, 3D point clouds and whatnot. What humans are not good at is seeing, say, a 360 image or having 360-degree situational awareness. So there are some advantages there, and humans also cannot detect range directly or measure velocity directly. I mean, we're pretty good at estimating that, but still, it's something that you get with some sensors. So some advantages that people don't really have or don't make full use of are things like prior knowledge, and I'll just condense that down into saying maps, and we've talked, quite a few speakers have talked about maps today. And then, of course, shared information through wireless communication, so DSRC and cellular. I am going to drill down a little bit on the prior knowledge here. Obviously, like I said, we could spend all day talking about all of these challenges. Because I think this is an area where we can talk about some of the successes and some of the ways to push the technology forward. And so just to be explicit here, for prior knowledge, I mean, there's a lot of things that we can talk about or group into there, but we'll just talk about maps for now. And one of the things that maps do, to be very explicit about it, is that it allows us to simplify some of the perception problems or the sensing problems. For one, it gives us an idea where to drive, for one, that defines lanes, defines places that are drivable, and also where to look or perceive things, where we should be facing our sensors. But to do this well, to use maps, there are actually some problems still that are not, I mean, there are certainly people that have solved this in certain ways, but it's still not stuff that you can essentially buy off the shelf as a product. So some of these sensing challenges include the registration of your perception to your map. So when you get a LiDAR scan, figuring out where that corresponds to the map, and the accurate or precise localization of your vehicle or your sensor within the map. Those are sort of two sides of the same coin. I'm going to talk specifically about the localization part, and we'll dig down into it. So, when we're talking, there are lots of cases where we talk as the stereotypical or sort of prototypical cases for localization or automated driving, and it's easy to find examples where normal approaches sort of fall apart. And I just picked a picture. This is something that I've used a little bit. This is the I-75-85 and I-20 interchange in Atlanta, because it's kind of interesting. It has almost all the challenges that are pretty well recognized, particularly for GPS, but there are also some challenges for these map-based localization systems. I'm not going to go through all those. What I want to get to is just a brief discussion about a system that we developed to do localization. In part, we developed this because there really aren't solutions on the shelf right now that you can just buy and you're done. You basically plug it into your system, and now you can focus on the other problems, the routing, the path planning, whatever it is. So our solution is called Ranger. It is basically, and it's a little hard to describe it fully, but basically all it is a camera facing directly at the ground underneath the vehicle. And a little bit, so I want to distinguish this from the thing that you might think about when I describe it. It's not an optical mouse where you're doing optical flow between images. It's actually an absolute measurement of location. It's matching images from a live camera feed to what you've stored in a map. And when you do this, you get some really good benefits. And I just want to mention, so this is something, again, we basically developed this to solve the problem for ourselves. We've seen the problems with trying to drive with GPS only, or even with lane detection. It's really challenging. So we've put this, these are just the vehicles that we have at the Institute, that we own at the Institute, that we've put this on, and there are more to come still. But basically what it allows us to do in terms of performance is really pretty good. We did some measurement of the actual performance. So this is, it's a little bit difficult to measure to validate the measurement performance, but so we didn't do that specifically. We actually looked, we have an automated vehicle. Actually, we'll point it out here, the 2006 Ford Explorer up there on the right, Marty. We actually took this on a course and measured the wheel placement on a repeated cyclic route in 10 different spots. And basically, when you look at the driving precision that you can get when you use this system, we actually measured plus or minus basically 2 centimeters for dozens of iterations through there. And you can kind of see in the bottom here, this is just this red line is basically what you get with the Ranger measurements, and the blue is just all the GPS points that we got in comparison. And this is just a blown up section of that. So I may be talking too fast, too slow, I'm not sure, but I just want to show, just to show you, putting it all together here. Basically, this is sped up just a little bit, 50%. But basically, yeah, we can drive this course. This is at our test track, and this is sort of showing you the process happening in stages. So eventually you get to this where you basically can match images, and it's quite reliable. It's very, very, very diminishing, or very small false positive rate, pretty much negligible. But it allows us to actually drive this course that we have out at Southwest Research through a set of cones that I can say that I have trouble driving through. The brush guard on the front of the vehicle knocks over cones pretty much every time I try and drive it myself. So this is just sort of an example of one solution to this, and I feel like given our endeavors to automate vehicles that saw that these types of solutions are needed in order to really facilitate. I mean, not necessarily this one, but these types of solutions for localization, for sensor registration, are needed in a more broad sense in order to facilitate the full automation of vehicles. So I think that is about it. I don't want to spend too much time here before the discussion.
Okay, do we have any immediate questions for Kris before we move on to Charles? Go ahead.
I'm just curious how, if we wanted to deploy that on a street where many cars and trucks drive over, how quickly do those signatures change?
That's a good question. So they don't change that quickly. In fact, that video that we had there, I mean, it is our test track. We don't have quite as much traffic there. We do drive this vehicle on there a lot, but the map that we used was a year old. So the weathering of the pavement, and it does weather, in fact. And we've seen in a lot of other cases, I mean, it's surprisingly robust to changes. I mean, things like water on the road and debris and whatnot. So degradation is pretty good.
Any other quick questions? Go ahead.
So were you saying that your vehicle would start out, let's say, with no information about the road, then as you drive to work every day, it would learn the map of the road you're driving on? Or?
How does the original map?
Yeah, that would be possible. I mean, we do manually drive either that vehicle or another vehicle with a ranger system on it to build a map. I mean, it's the map building process is pretty automated, but you do have to drive it an area at least once to generate the map.
But how do you determine the absolute location of the features?
That's a good question. So we do reference it to whatever the absolute, so GPS typically. It's not really that critical for the purposes of automated driving to have a very accurate GPS. But if you want your map registered really well in an absolute sense, then the better your input to that, the better your registration will be.
Okay. Thank you, Kris. Yes. Charles, if you'd like to come up. So we're happy to welcome Charles here. He is the Vice President of Marketing for RF and Wireless Solutions at National Instruments, and will give us a good presentation leading into the panel session.
All right, thank you very much. Thank you for welcoming me here today. A little bit about National Instruments. Many of you may know us as a test and measurement company, but really founded on the mission of providing tools and systems for scientists and engineers to accelerate productivity, innovation, and discovery. And this is certainly an area where there is a lot of innovation and discovery happening. At $1.2 billion of revenue and 40 years of existence, we've been helping engineers solve problems for a long time. Today, just to give you a simple example of where our primary interest is in this space, just to choose a simple IoT example is the thermostat. 15, 20 years ago, a thermostat used to be a bimetallic coil, largely a mechanical system, if you will. Now, if you look at a modern-day thermostat, it's integrating a ton of wireless technologies. It's connected to the world. It's using intelligence for the promise of, number one, being an awesome experience, but number two, helping us improve our lives through energy savings and so forth. The other interesting thing about the thermostat, though, is the thermostat I had prior to a Nest had the same features for 10 years. My Nest is updated about once a month with new software, and it's the software that defines the functionality of the system itself. It's a little bit of a different testing challenge to test a software-defined thermostat that's changing its behavior every single month than it is to test a bimetallic coil. So if you begin to broaden that to what's happening at a much grander scale in the connected vehicle, you do see a number of different similarities. You are going from a largely mechanical system to a largely electrical system. You're going to one that was isolated from everything else to one that's depending on something else. And more importantly, you're going to a system whose functionality is defined through software. And it's not just software on one CPU, as we heard earlier today. It may be 100 CPUs networked together using different algorithms and features to make decisions that influence and impact your safety as a consumer. A test and measurement company's job has been to generate the stimuli and measure the response on a component level basis. We're really good at testing hardware, but as a test and measurement industry, we are needing to learn a lot and discover a lot about what it means to prove the safety in the billions and bazillions of possible combinations of 150 processors running independent algorithms that are changing monthly. No one talks about a 2015 model Tesla because the Tesla's always changing, it's always being updated. And in the anecdote we heard earlier, Tesla deciding to change how they fuse the data from multiple sensors together can impact people's lives. So these algorithms do have to work in coordinated ways, and they do have to be proven in the lab in a way that works. I'm going to skip a couple slides in the interest of time here. National Instruments has been a company based on a platform for many of years. And what we do is we take modular instrumentation hardware where you can assemble all the I/O points you want. We put that together with LabVIEW system design software that allows you to create multiple different scenarios. And this becomes really important as the backbone for a solution of testing systems of algorithms in vehicles, because it allows you to take a FlexRay module or a CAN module or a new Ethernet Plus module or a radar RF in the 77 gigahertz band, any different signals from cameras, and be able to put together any system as a combination of sensors, even as those sensors change. And then, of course, because we don't know what the simulation and the sensors are today, you need the flexibility through software to be able to adapt to any situation. So we began an effort about 18 months ago in working with a very small number of customers. Audi is the one that's public. And working with Niels Koch, who is the director of radar systems at Audi, on how do you build and extend hardware-in-the-loop technology that's been used for the mechanical parts of an automobile to include GNSS, to include radar, to include positioning, to include LiDAR, to include video, with a focus on the radar piece. As Rodi and Schwartz mentioned, radar is becoming an incredibly critical part of the technology. But there's also the challenges of all of the interference, the spoofability. How do you create these different scenarios of different vehicles on the road? And so what you can see out there, we've been working with UT Saves on trying to create a system that allows us to experiment with the testing of these radars, the ability of that software to sense, to compute, and to act fast enough with all the combination of software algorithms and network latencies in the vehicle to produce a vehicle that's safe under all of the changing circumstances that we're going to face in testing systems of systems where software defines the functionality.
You caught me off guard, Charles. I didn't know that was the end, and then it was the end.
The end.
The end. Thank you. I asked Jianming Ma to come and give us some perspective from the Texas Department of Transportation, most particularly in infrastructure. Tell us what kind of sensing is going on in infrastructure and how that sensing can improve the performance even if we have low level of penetration of connected and automated vehicles. Let's make sure yours gets pulled up here. Great, you're good to go.
Thanks, Todd. Good afternoon, everyone. I'm very pleased to be here to talk about infrastructure-based sensing in the connected vehicle environment. So I've heard great presentations from a lot of speakers. I learned a lot. I believe this conference is touching on some of the important topics related to connected and automated vehicles. So basically my talk, I'm going to from a different perspective, infrastructure owner's perspective, or operator, if you will. Basically, what I'm going to talk about today, including 2 points. First, describe infrastructure-based sensing and the connected vehicle environment. Then the second is to help you understand that infrastructure sensing will remain critical for connected and unconnected vehicles. So let's start with a brief introduction about of infrastructure-based sensing that has been widely used in transportation. So the first column lists out some infrastructure-based sensing technology. The phrase infrastructure-based means that these sensors are installed at fixed location in the field. It is a little bit different from what we heard earlier. A lot of speakers talking about vehicle-based sensing. So the first row shows some data elements that these infrastructure-based sensing will be able to give us. And so in terms of connected vehicle environment, basically connected vehicle are, they are like ability of vehicles of all types to communicate with other vehicles, infrastructure equipment such as traffic signals, to support a wide range of safety, mobility, environmental applications of interest to both public and private entities. This concept also extends to the aftermarket devices brought into vehicles, to pedestrians, to cyclists, or motorcycles, or even transit users carrying compatible devices. So collectively, all these elements form the connected vehicle environment. So envision that in a fully connected vehicle environment, so the traffic signals will be able to know the status of every vehicle on all approaches at signalized intersections, and thus will make optimize the signal timing and the plan. And we have a lot of other strategies that Dr. Peter Stone mentioned for the signalized intersections. And traffic management centers will be able to monitor real-time traffic conditions, and by using the data from a basic safety message broadcast from connected vehicles. So, but as previous speakers mentioned that what is market penetration rate now? It's 0, right? NHTSA, National Highway Traffic Safety Administration, which is a government body for the vehicle safety, they haven't released a mandate yet. But according to a recent release, press release from White House, it was dated September 19th of this year, the day before they announced a federal automated vehicle policy. It says DOT will soon be released a mandate that requires vehicle OEMs to equip their vehicles with V2V communications. And this curve is from a study that Virginia DOT has done. Basically, it put up some projections about CV market penetration, and also US DOT project that by year 2045, the CV will reach 95% of market penetration. And as we can see, it's going to take a long time before we reach the full market penetration. So what are we going to do in this long time, during the transition to the full CV market penetration? Let me just give you a few examples that infrastructure-based sensing is going to be critical in helping us to transition to the CV full market penetration. For example, this bridge heat warning. I know we have some low clearance bridges on the highways. So if this vehicle is an equipped vehicle, so the roadside unit will be able to tell its bridge is too high to pass the bridge. If it's not, we have to rely on the infrastructure-based sensing to tell us, if it's too high. And similarly for this runway driving application, so if this vehicle, this runway driving vehicle is an equipped vehicle, so the roadside unit will be able to tell through like V2I communication if this vehicle is driving runway because it broadcasts a BSM, which has like a heading information. And if it's not, we have to rely on some like infrastructure-based sensing to tell us. This is another example. Basically, it's the curve speed warning application. It also needs some like infrastructure sensing to tell us like the roadway conditions as well as like temperature, freezing temperature, in order to alert drivers on a curve. So as we can see, just like the infrastructure-based sensing has been widely used in transportation, if you will. And in a nutshell, that infrastructure-based sensing is going to play a critical role before the CV reaches full market penetration, because we can even get some early benefits from the low level of CV market penetration, as the infrastructure is able to sense unconnected vehicles and relay information to the connected vehicles. Even after the I want to say even after the CV reaches 100% of market penetration, we still need the infrastructure-based sensing to aid us in verifying the claims made by the connected vehicles. And otherwise, we're going to have some security issues because of inside attacks, like some like bad players, just like our internet security. I mean, there are some bad players over there, and we learned lesson from the aviation industry. We thought a transition to next gen, which is a GPS-dependent system, would allow us to eliminate like a ground radar around the U.S. and near airports, but due to the security concerns about the GPS, so we cannot eliminate those. With that, that's just a very short, quick overview of infrastructure sensing in a connected vehicle environment. Thank you.
Excellent points. We can't do away with the infrastructure sensing even if we get 100% penetration. I'm going to turn over the moderation of the panel today to my colleague, Robert Heath. He's an expert in sensing, as many of you noticed as he gave his presentation earlier this morning, and he'll grill our candidates, or I mean our panelists, and too much in the throes of the presidential cycle, I'm afraid. And of course, you're welcome to ask questions from the audience too.
All right, great. So I was sitting there thinking, is the panel going to start at some point? We're going to ask some questions. So now is the time. How much time do we have for questions? 2-3 minutes or 20 minutes? 20 minutes. All right, gentlemen. Does anyone in the audience have a burning question? Yes, Constantine.
I'm curious, back to you, Kris, and what kind of map I would have to store in order to drive around, say, just Austin.
Like the size of the map?
The size of the map and the resolution. Are we talking about something big or?
Well, so there's some flexibility there. Now, we've developed it sort of as a development system or a prototype system for us, and just looking at the size that we typically get, and this really depends on how you sample it and whatnot. But we typically see, if you're just looking at the features or the core stuff that you need to localize off of, it's about 100 megabytes per lane kilometer. Now that's completely uncompressed or unoptimized. We do estimate, and we haven't gone through the process of actually compressing or attempting to compress it, but that we may be able to get all the way down to 1 megabyte per lane kilometer. That's being really aggressive, but then,
This is using no GPS, just pure signature from the concrete.
Yes. Yeah, in fact, it's kind of interesting. So having actually used it, and it's part of our systems, we found in some cases where GPS has not been configured right, hasn't been actually connected in the system correctly, and so we're actually just driving purely off of the Ranger system. So, in principle, it works like that. I think conceptually, it works as part of a larger, holistic approach.
I want to jump in here and ask kind of a related question. I mean, Charles, we've been working on this this radar hardware-in-the-loop platform. And so I'm thinking now, with all these different sensors, I mean, do you envision having like a room that has, we could have a texture emulator, we could have camera emulators, radar target emulator. I mean, is that sort of what you see for testing cars at the end of the day? And granted, you're going to sell all of those products too and make a boatload of money, apparently.
So, I mean, we're in a learning phase. If we weren't, we'd have a standard product as opposed to a relationship with right people. But there's three ways you can try to prove out these systems. You can do it purely in computer simulation. We saw some of that earlier today. Really fast, a lot of different scenarios, tends to be very pure and not the dirtiness of the environment is dependent on the model. On the other hand, you can build a road test and you can test things in the real world, but it can be expensive, very time consuming, and very difficult to produce all the different scenarios you want to reproduce. So we do see an opportunity in the middle with this hardware in the loop where you can emulate electronically the physical world and the situations you can be in, and what happens if you get multipath interference and you lose GPS for a little bit, or can you add to, by fusing this sensor and the two algorithms working together, can you create something new? So we do see the possibility of there being a room full of configured, an anechoic chamber, if you will, where you control the environment around the vehicle with both RF technologies and sensor technologies. But the limits of that, where its usefulness is, how many sensors you need, how many standard use cases you can have versus how much configurability you need to simulate any situation, these are the areas we really want to explore through relationships like we have with UT Saves.
Okay. Excellent. Yeah, thanks for that plug there. Haha. Yeah, question, Sue.
For the government to incentivize users to push connected vehicle technology in the car to be able to benefit from the infrastructure side, I heard earlier one of the audience mentioned maybe giving them longer green light time, or some other people may be thinking HOV lane use for vehicles with this technology. Would this be under Texas DOT's consideration when you roll out infrastructure, but also giving some privilege to early adapters on the vehicle side?
Thank you, Drew. I think
So we're rolling out the easy questions, clearly.
I think that's a great question. I guess I think it's a chicken and egg issue. I mean, since federal hasn't released a mandate yet, vehicle OEMs they're waiting on it. We also are waiting on it because if there are no vehicles, I mean, we probably won't be able to put like an infrastructure on our roads, and so. But I guess there are a few strategies we could just do, and from the for example, recently AASHTO, the American Association of City Highway Transportation Officials, they put out we call a SPAD challenge. SPAD means signal timing and phasing, signal phasing and timing, if you will. SPAD challenge is just a challenge each state to deploy DSRC equipment on like 20 intersections for 50 states. That's going to be like 1,000 intersections. So that way, OEMs will have like incentives to equip their vehicles to talk to the signals. I think that's just one way, but we're still assessing the other options that we could to expedite and the deployment process and get early benefits of it.
So I want to jump in there because I had a related question. I keep hearing this chicken and egg problem here, and I'm just kind of scratching my head what's left of the hair here. And why? I mean, can someone in the state of Texas just say, okay, all cars sold in Texas have to have, DSRC? I mean, just solve the problem. I mean, can't we just solve it? Because Honda and Toyota are like, they already have the products. They're just sitting around waiting for everyone else to do it, apparently. That's what everyone's doing.
In economics, we call this a collective action problem. It's not a chicken,
Yeah.
it's called collective action.
But we're talking about, I mean, all the value is in saving lives, and yet everyone's kind of waiting for everyone else to start the saving. So what am I missing here?
I think that's a great point, but it's way beyond my. I can't answer that question. I mean, it's up to the legislative. I mean, a lot of times, you know, the state legislative, they have a, you know, they have like a bigger picture of what, you know, what should be doing. And
I follow a lot what
yeah.
the state legislature does, so
Yeah.
maybe we should discuss that offline. All right, so audience questions. All right, hey, okay, someone over here on this side, because we're not picking anybody up over here. You all sitting in the dark here? You all have some questions here? Yeah, all right. The question back here.
What you guys were saying about DSRC and
Okay. All the sensors, they are working very well when you're buying a car new. And TxDOT, I mean, I believe you are the official who's doing the state inspections. So if my car is 5 years old and I've had an accident, the bumper is a little bit roughed up, what kind of methods and ways are you making sure that all the sensors are working in 5 years?
Wow.
Oh.
I don't even know I'm representing that that official, but anyway, but that's I think that's a Texas DMV question, but you know we're yeah we're just responsible our maintaining our roads, you know, the vehicles. That's I can't answer that question either.
Okay, so yeah, question.
I mean, I think that's a great question, and I'm wondering, is it directing at all? Is the question of how expensive is it going to be for me to fix little bumps on my car? Is that directing how we're thinking about what sensors we're going to have? Because I could imagine that it's different. As someone who smashes my iPhone on a regular basis,
That is true. You're on your third screen or fourth screen now?
And just one question on that, or a comment on that, because at least here in Texas we have inspection, but what I understand in California they don't have any state inspection. So I think it needs to be named.
I think they have much more there. They have emissions, all kinds of inspections there.
I don't think it's a safety inspection per se.
Yeah. Okay. Yeah. It's environmental inspection.
Correct.
Yeah.
Yes, I mean, from my perspective, I think on the development side, obviously we can sort of wave our hands and say, you know, that will be dealt with when these things go to production, right? But I'm part of a group. I've been sort of lucky that I haven't done it myself, but our group has destroyed a lot of sensors. So you know, we're keenly aware when you destroy a $20,000 sensor or something that's something that you have to consider even a little bit up front. I mean, so the idea that you have a giant spinning LiDAR on your roof, and as a human driver, you don't really necessarily have a good sense of the clearance of your vehicle. That's you know just asking for trouble, and we've had that trouble before. So I mean, I think you know looking beyond that. I mean, I've had the question you know posed to me, particularly because we're putting a camera under vehicles. Like, how likely is that to get just damaged, covered with mud?
Or how do you keep it clean? By the way, we were discussing that.
I mean,
earlier.
I have to say that you know we've driven a lot, so we don't do anything special. We just through experience. This is empirical results here that we have never cleaned any of our lenses.
Do you ever drive it in the rain or the mud?
Yes, we drive it. We drive it a lot. I mean, we on our I don't know if you noticed, but we put it on our Humvee. I will say that has gone a lot more places where it's mucked up the lens, but we haven't used it quite as much in terms of development. But I've actually been very surprised. You know, having actually looked at you know what you get from these cameras, you know, I've spent a lot of time looking at pavement. I've spent a lot of time actually looking at the undersides of vehicles, and there's a surprising. It ends up being much better than I've expected. I mean, you know, once you start getting these out in large numbers, then you'll see probably the effects that you know we don't see in the small test sets that we get. But
All right, so
There is a
audience, more questions here. Looking here. Okay, so I'll ask a question in the meantime here. Do you all have any sense of how much, like how the networking inside the car is going to change to evolve to support all of these new sensors?
Is the CAN bus dead?
Yeah, is the CAN bus dead? Do we need fiber in the car? Millimeter wave? What's the deal?
well, I don't know if you guys want to answer, but so I don't know that the CAN bus is dead. I mean, it still serves a useful purpose, particularly on the vehicle control side. But it's clear that you can't use that for others for most sensing modalities. So already pretty much everybody is running Ethernet cable in cars and using Ethernet for a lot of communications. I don't know. Actually, we've never. I'm aware of FlexRay as a as a communication method, but we've never used it. So I'm not sure what the next step will be or what the next generation will be. But for now, at least, certainly on the development side, there's a lot of Ethernet cables being run.
Yeah, I think I agree. Exactly, CAN is not dead, but we will see the rise of higher speed networks. But we need to have higher speed networks with latency that we can tolerate. Part of it is I'm not exactly sure how much data we're going to be shipping yet. If you're a company that sells large processors, very powerful processors, you want as much sensor data in so you can sell a big processor. There are other companies that prefer a more distributed model where less data is going back because more of the processing is handled in the nodes. And I think there's a debate right now about where the best place is to do that processing. A lot of data in one place, so you have every possible piece of information can make a best decision, or localized good data just sending back, say, distance and number of targets and smaller amounts of data like that. And depending on how those algorithms partition across the vehicle, I think will drive the need for buses with different characteristics.
Yeah, I agree with them. I guess nowadays, like an average vehicle, they have probably like 50 to 100 sensors on the vehicle. There are going to be a lot of data flowing around. I guess one option would be like you can just grab all the data from the vehicle and transmit it to whatever it needs. And another option would be like probably edge computing. Just process the raw data and then get useful information and then send that back. I mean, it's just my opinion.
All right, excellent. So some audience questions here. All right, Todd, get a question over there.
Yeah, okay.
Wait, hold on. There's one in the back there, or two in the back there. Run, Todd.
I can just yell
Okay.
All right, yeah, that's pretty good.
Infrastructure. Hey, do you see there being a day when the infrastructure sensing could alert things like law enforcement or emergency services to say like, hey, there's something going 150 miles an hour down Mopac, where there's something that came to zero very, very quickly, and that's a wreck. So do you see that kind of stuff happening in the near future?
Actually, you're talking about traffic incident detection. Basically, nowadays we already use some of the data, for example, speed flow data, and on just on a map. Just if, for example, if there's like on a certain segment of road, and one direction there's like a green segment immediately after the red segment, that means there's something wrong with that spot. So we can just use other means like surveillance cameras to check. And I mean, I guess in a connected vehicle environment, and we'll be able to accomplish that pretty easily.
All right, I think we had another question back there, right?
Yeah, thank you. Okay, so you've got replacement cycles on cell phones. We talked about smash ones there, on PCs and so forth. Quite a bit different than on vehicles, which has a really robust secondary market. How do you foresee, everything's dependent upon ubiquitous deployment of these vehicles, if everything's been described today. If you don't have a secondary market, I mean, who's going to buy a used autonomous vehicle to support that? It seems like there's a major hole kind of in the market of how you get to adoption on widely deploying these if there's no secondary market for autonomous vehicles. Does that make sense?
I'd buy a secondhand autonomous vehicle. I don't know. Anyway,
What
sorry,
is the-
panel, please.
What is the theory behind there not being a second market for autonomous vehicles?
Your upgrade is on the sophistication of the software and the sensors and everything. It's like you don't have people buying new cell phones widely or buying new PCs. Everything that's bigger, better, faster. But the same thing going on with the vehicle.
Oh, yeah.
There is a dichotomy there with the secondary market for
So-
those vehicles that exist now.
yeah, the technology becomes kind of obsolete because it becomes so much better later. Is that the point?
Is there going to be a market for the 2015 Tesla 5 years from now, right? Because it's known to have an inferior sensor suite.
Yeah, I think that's a good question. As somebody who buys used cars rather than new cars, I feel like I'm in the category of somebody who would be more than happy to buy a used autonomous vehicle. But I mean, I think the point's valid that you know, if you're buying inferior hardware from the outset, I mean, maybe your expectations will be out of line. But I would say that I would expect that there to be a pretty vibrant market there still, but I honestly don't know. Can't predict.
Yeah, I mean, I guess we're all kind of guessing now because this is pretty far out there. I do think that there will be a part of it where you'll have outdated hardware technology or you'll want something new, but that's the case in even new cars today. I mean, you always want the new gadget on your car. But I do think we're going to have more rollout of software upgrades and making use of the sensors that are in vehicles. We're not talking about a million different kinds of sensors here. We're talking about cameras and radar and LiDAR and GPS. Once you get a functional basic set, there's probably a lot you can do with it through software upgrades. Now, is that universally true? No. Now, I would also argue that there's not a secondary market for cell phones. Maybe not here in the U.S. primarily, but I think globally, if we think globally, there may be markets outside of the U.S. if people here only want the new shiny Cadillac with the latest release.
Right, excellent. Todd, how are we doing on time?
We've got about 1 more minute.
1 more minute. Is any audience question? Oh, there's one back. Yeah, shout it out.
Do you expect this to initially come out with an initial sensor certification process? Or do you see it almost like calibration of test equipment, where you're constantly having to recalibrate your car and its sensor?
Ooh, excellent.
So there isn't a set of emerging standard ways. Let's just talk about radar for a minute. System level, it just gets wide open. But so a radar module today is a transducer and a piece of software. The transducer was great talk by Rody before this one on qualities of the transducer and how to make measurements on the quality of the transducer. It's the software quality then that becomes part of the unsolved problem. But there are a growing number of use cases that are used in standard ways where you can play back waveforms from test and measurement equipment today, or you can make measurements from test and measurement equipment and put it through pretty standard scenarios. But those things are always evolving. You know, if you have a crash or something happens in the field, you want to reproduce that exact scenario and make it a part of your test suite. So will the test suites grow and continue to grow as we get more use case and more data, and as the software changes inside there? Yes. Do we have a massive testing burden that we'll have in the future that we don't have today by testing not just hardware revisions and upgrade cycles, but by testing every new push of software? Yes, we will, which is why it's an area that I think the T&M companies have got to be doing research on and figuring out how they're going to keep up with that change in demand and the way that the vehicles are developed and released to market.
One more brief question, if you will, Robert. This is for Jianming.
Oh, perfect.
Earlier this morning, we talked about government agencies, departments of transportation offering rights of way so that private entities could co-locate sensors on these rights of way or transmitters, and maybe be beholden to the government for offering additional services to drivers. So, for example, if I'm AT&T, I put up a wireless transmitter, an LTE network, but now I also have to put up something that listens to DSRC. Have you been entertaining these questions for basically a public-private partnership for developing the infrastructure required for connected vehicles?
I think that's a good question. I think public-private partnership has been used in the transportation industry, you know, at the toll roads and other things. I mean, it's not new to transportation industry, but you know, for this connected vehicle, autonomous vehicle area, I'm sure there are going to be some collaborations between the public sectors as well as you know, the private sectors. So we probably need to find a a new business models that can incorporate all the resources that public agencies have, as well as the resources that the private entities can offer. For example, the public agencies own the right of way on the road, so we probably can leverage that resources. I mean, those resources. I mean, to have the private entities to participate. Private communications and other means. I mean, I think that's definitely a new business model that we need to explore.
Yeah, I think it's one of the most exciting things to
Yeah.
to be mentioned today, and I'd really like to see that part of the Texas Department of Transportation's portfolio going forward.
Yeah, absolutely. So I guess we got to wrap it up now. So panel, thank you for your wonderful questions and answers.
For moderating the panel. We'll now bring up the